Yeah, it's one on.
Thursday.
Okay, so I just.
Okay, that's e-classes.
Oh, okay.
Yeah, e-classes, I have to change it. 4.2 is gonna be Thursday. Yeah, so let me get my document open and I'll write it on the document.
Yeah.
4.3 outline due on Thursday.
Okay.
No, 4.3.
Yeah.
Okay, so I'll write it right here, all the information that you need. So, Tuesday, April 14, research day.
Does that just mean like you have to research or
No. You have to go watch somebody present their research.
where?
So it's 2:45 to 4 p.m. Go to a different one. Daniels Hall, 219 is the, I think, where's
But
my,
it's on Tuesday, it's on the class, so.
yeah, we don't have class. This is why I can't have class. I'm gonna be gone. I think it's Daniels Hall 219. I have to double check this part right here.
Wait, is that the only one you're going to?
This is the only one that I am going to be at, but if you go to a different one, then take a few notes of the presentations that you attended. And you don't have to write anything huge on it, just 3 or 4 sentences on a piece of paper, handwritten, just so I know you went to it. And I'll give you your 5% extra credit to the quiz.
So they go all day long.
They're all day long, yes.
Are they like one after another, or are there some that are at the same time?
There's a whole bunch of them all at the same time. And then they start at 8:30 in the morning and go until 4 o'clock in the afternoon. So there is bound to be some that you can go to sometime in that.
So you're going to that one?
I'm going to that one. I have to. My seminar students are presenting and it's their final grade. Yeah, that one will be math. I think it's 8:30 in the morning. If you go to the library webpage has a research day schedule posted on it. Into 4. Daniels Hall is a social work building, but it's where they have the most free classrooms in the afternoon. That's why we're there for the math one. But they're all over campus at all different times. You don't have to go to the math one. You just have to go to some research presentations.
So there are these that are like, are they all that long?
They're broken up by the way they have it is they want you to go and stay the full time, but there's multiple sessions. So there are going to be 4 presentations in that time of 15 minutes each, with 5 minutes in between for setting up the
Can I go to
research.
like that one after I get out of my other class?
Or do you want us to go for the all hour and 15?
Because I have class or work.
Go to as much of it as you can go to. Yeah.
So we have to go to the whole.
Just leave.
As
leave
much
it
as you
out,
can.
leave it.
Yeah. I mean, as much as you can go to. I know you guys have busy schedules, but
So in good twice, we got 10%.
no. 5%. 5% extra credit. Yeah. To the overall quiz grade, so I'm going to be adding 5 points. It'll look like it just says 5 points, and it'll look like you really didn't get many points, but it's
That
to your
can be-
overall score. It's not to the average when I
Oh.
put it on your class. Yeah. So
I
it'll.
think that 15% like going just.
No, I don't want you skipping classes. No, 5% extra credit to your overall score, not to a particular quiz, but this is your overall quiz grade. So if you currently have a 90 on your quiz grade, so you have a 95. That's how that's going to look. Yeah.
I never get 90 on a quiz.
Yeah, and when you go to a presentation, if it's already in progress, wait until the presenter's done and they're getting the next presentation set up. That's when you can go in and out of a room. So don't enter a room in mid-presentation, you'll mess up the presenter. And that wouldn't be good. They're just students. They're not
Just like
used to being
music.
interrupted. What?
So just like music, you wait till the
Yeah,
song.
just like music. Wait till the song is over before you go in. Mhm. That's true.
So it sounds like, but not more sense.
And see if there's something you can ask a question about at the end, because they're getting graded on answering questions. So, yeah. So, yeah, see if you can come up with a question. They're allowed to say, I don't know, if they don't know. But come up with a question, because their
Well, they're gonna get
interaction with you
credit.
is part of their grade, and so they need an audience.
Class, is that what
All kinds of different, this is math seminar, but there's all kinds of classes that are presented. Yeah,
But that time period right there is.
that time period in that classroom is math.
And you got a presentation at the panel, something on a student.
Those are all students gonna be presenting that one. But, do what?
We get out of, I was thinking, we get out of here, I'll do that.
Yeah, make it there for as much as you can. Mhm. Allergies have got me today. I feel bad for you. Oh, it is. Okay, let us talk about section 4.2. We're talking about functions here. We have a couple of definitions on this first page. So for a function f that takes a to b, the inverse of f is a relation from b to a. What's the difference here? They still have xy, but so that yx is an f. So you just flipping it, yeah. Notice they call this a relation, not a function. Don't call the inverses functions until you prove they're functions, because there are many inverses that are not functions. So be careful when you're doing that.
Especially as
Especially what?
U-shaped.
Yeah, parabolas. Okay, for the function f that takes a to b and g that takes b to c, the composite function of f and g is relation from a to c, and it's written as all xz in a to c so that you have a y in b, xy is in f, and yz is in g. This looks just like the relation composition that we did in chapter 3. And there's no difference other than we're specifying that it has to be functions that we're starting with. Okay, now let's look at an example here. F is going to be the line y equals 2x plus 1, g is y equals x squared. They are mappings, their domain and codomain are the real numbers. Find F inverse. Interchange x and y. So if we interchange x and y, you have x is equal to 2y plus 1. So x minus 1 is equal to 2y, or y is equal to x minus 1 over 2, right? Do you remember doing this for relations? Yeah, exactly the same thing. Is this a function? Straight line, it's a straight line, right? So this one is a function. Let's look at G inverse. What is that one going to be? How about plus or minus? I need to get the equals in there. Y equals plus or minus the square root of x. Is that a function? No. How do you know? Yeah, it's a rotation. It's flip across y equals x. But what happens? Yeah, it doesn't span the whole domain. And the plus and minus right there tell you vertical line test. Remember that from before? So, two problems. Our vertical line test we had talked about in our definition of functions. So it's not a function because it fails a vertical line test.
That actually gives like an explanation.
Well, what you would look at is that
Like in a proof, would we actually say that it's a
no. Yeah, so let's give it particular x values. So you know, if we use 4 for x,
It gives you two Y values.
yeah, 4 plus or minus 2
Yeah.
is in G inverse if we're not a function. So when you're trying to show something is not a function, give me particular numbers. Don't explain it. I know it's easy to explain it, but give particular numbers. That's what we do. Yeah. Oh, okay, that's fine. Now, find F composed of G, find G composed of F. So, what is F composed of G? Yep. Y equals 2x squared plus 1. And how about G composed of F?
2x plus 1 squared.
Yeah.
Oh,
That little circle is composed. So it means you take the right-handmost one, plug it into the left-handmost one. So this is the same thing as
Yeah.
f of g of x, which you recognize from pre-calculus.
I'll do that.
That bracket should get finished. So tell me, which of these are functions? Both. Both are functions.
Yeah.
Yeah, they're both parabolas, just one is shifted to the right and the other is shifted up and down. So they're both parabolas, so they both are functions. Any questions on that? Okay. How do you show that a relation is a function? Remember, there's two things we have to show. You remember from the definition? Domain of F is equal to the set. Yeah. XY, XZ, and F tell you that Y is equal to Z. Those are the two things. And so when you're reading over this, you saw them checking that like multiple times in all the different proofs. You should have gotten to the point that you were recognizing, okay, I don't know what just happened. Let's see. Oh yeah, there we go. I clicked on that. So what you have, they were verifying the domain, and then after they verified the domain, they'd verify
Y equals
y equals z. So that's the two steps that we have to verify when we show that something's a function. Okay, this proof I wanted to do is a very important proof. They actually did this in the book, so you should be familiar with it. If we were doing this proof, it says show that G composed of F is a function and from A to C, and then show that the domain of G composed of F is equal to A. So they kind of broke down the definition of showing that it's a function. When we're showing that it's a function, this part right here, they mean if you have x, y, and xz in F, G composed of F, sorry, I forgot about the G part, then you know that y is equal to z. The y values have to be the same. So, and then the second part was showing that the domains are the same. So how would we, let's look at showing the first part right here. Productor. How would we show the first part? How do we show that G composed of F, for the x, y, and xz parts? What do we have to assume? We have to make an assumption, right? Let x, y, and xz be in G composed of F. Then we have to figure out that y equals to z. The only way to know that y equals to z is to know some relationship about y and z and where they live. So we have to apply the definition of composition. So then that means that there exists, what would they call it in this proof? I don't remember. There exists a W in, let's see, F goes from A to B and B such that XW is an F and WZ, WY is in G. But that's for the XY part. Yeah, but I can't use the same variable, so we have to, there exists a U in B such that XU is an F and UZ is in G. But what do you know about F? So you have XW is an F and you have XU is an F. We assumed that F was a function. F and G are functions. So if you know that F and G are functions, yeah, W and U are equal. And as soon as you know W and U are equal, then you have a WY and a UZ in G, but you know that W is the same as U, so you have a UY and a UZ in G. What does that tell you about Y and Z? Yeah. So that's how we prove that. You guys want to see it typed up? You okay without it typed? How about everybody else? You want to see it typed up or not?
No.
No? Okay, we won't type it up. It was. They did a pretty good job of it. Tell me about the domain of G composed of F equals to A. How do you show that? Those are sets. How do you show equality of sets? Subsets. So you have to show domain of F composed of G is a subset of A, and A is a subset of domain of F composed of G. G composed of F. I switched it on the quiz too.
You did. Totally confused me. I don't remember the let me know.
I totally didn't mean to do that. I'm just so used to F composed of G. That's the order we do it in calculus. Okay, so how would you show domain of G composed of F as a subset of A?
As
No.
long as you did the
If you got the relations right. And if you did it the right way, the way you memorized it from the book, that's fine. I can figure out what you meant. I'm good with that. How do you show the domain of G composed of F as a subset of A?
Well, the domain of F is A.
Yeah, so you have to start with X in the domain of F composed of G, and G composed of F. That says you have an X, Y in G composed of F. Apply the definition. So that says there exists a C in B such that XC is an F and CY is in G. But as soon as you know XC is in F, that tells you X is in the domain of F. But the domain of F was equal to A. That's what they told us in the proof, in the definition. To go the other direction, you're just going to choose something in A, realize that it's in the domain of F, so you have an X, Y, and F, and that because it's in the domain of F, then your function composition means that you can apply it to something that's also in G. So going back the other direction is just the same way. You're just not quite the same enough that you can say similarly. So are there any questions on that? We could do that one on a test? Yeah? Okay. If we study.
I know how to do stuff.
You should feel relatively confident about subsets about now.
See, I can do rec
No.
proof and.
I can do check proof too.
Yeah, rec proof, I can do. The subsets, I can generally do. Some of the other ones.
Yeah, that'll come. We just got to give it time.
I know how to flow, but it's, I
Yeah.
wanted it out.
All of the rules is why something does something.
They become overwhelming after a while.
And I am not good at.
I felt like a test. I was just like, I don't know how to prove this. This is what I think. I'm pretty sure I'm wrong.
Hopefully that doesn't happen much anymore. Okay, this one we should be able to do. This is just function composition. Can we do function composition?
Yes.
So what is H composed of K? Sine of x squared plus 6. Mhm. What is K composed of L? That's the same thing as e to the 2x plus 6. Yeah. And then what is L composed of H? Yeah, that one looks pretty ugly. It doesn't matter what we give you. You can just plug it in. Yeah. Function composition. Yeah, homework poems asking about that. That's the only example of that one. Yeah. The next one's a little more entertaining. I like the next example.
Oh,
Yeah, I told you it was a little more entertaining.
this one's not.
No. Well, you have Z6. Remember we talked about that. That's 0 through 5 in our modulus classes. And Z3 is 0, 1, and 2. And they use the two different notations so that you wouldn't get confused about which class it came from. Yeah.
So the line above it is, what does that
It's the
say?
same thing.
It's modulus. It means the same thing. But they didn't feel like writing down the subscripts of 3 each time. And then this would be like 1 mod 6 and then 2 mod 6 and then
Oh,
Yeah.
They just did different forms.
5 mod 6.
right, because
The chapter there's like, the line over you can do the
box,
graphics.
okay.
And you'll find I like the boxes better than the lines. You what?
Isn't this numbering necessary?
I still didn't hear you.
This needed to drop down there. Isn't that necessary?
Well, no,
They're
because
saying see that three right up top.
The reason for this is so you can tell which
That has Oh, that makes
No.
sense.
they don't. This is why I always use the boxes. Yeah. Yeah, so then if you looked at this first one, this would be 0 mod 6 is equal to 0 mod 3. That's what they're trying to say.
Yeah.
This would be 1 mod 6 is equal to 1 mod 3, 2 mod 6 goes to 2 mod 3, and so forth. So 3 mod 6 goes back to 0, 4 mod 6 goes to 1, and 5 mod 6 would go to 2.
Okay, I don't understand.
That's our H function.
Oh, yeah,
Mm-hmm.
yeah.
It's 5
So,
You go back to 3 or 0.
yeah, 3 goes back to 0. So if you want a different way of looking at it, you can do 0, 1, 2, 3. Oh, I'm going to run out of room. I have to move it over. Sorry about that. 0, 1, 2, 3, 4, and 5. And then this goes to 0, this goes to 1, this goes to 2, then this goes to 0, this goes to 1, this goes to 2. So you can kind of think of the function lined up this way. That might make a little more sense. And that's actually how we line them up in abstract algebra when we're talking about those functions. So here's a question. We do the same thing for k. K takes z3 to z3. 0 goes to 0, 1 goes to 2. It's interchanging 1 and 2 and 2 and 1. They just wanted to. But then they wanted to do k composed of h.
K is the
These are going from 3 to 3.
So it doesn't really matter.
Well, 1 goes to 2 and 2 goes to 1. So here's a question. What's K composed of H?
1 mod 3 is 4, 2 mod 3 is 5, right?
No one said that. What? Say that again?
I'm confused myself. What the hell is this?
K starts at Z3 and goes to Z3. It doesn't start at Z6.
Right.
H starts in Z6. K is a function.
Some-
It's like f of x equals 2x.
okay.
So K mod H, we want to know what this, first of all, what are the input values? Is it Z6 or Z3? Yeah. Okay, we have two different, here's a question.
Because your X value is always from 8% of
Yep. It has to go from where the H values start to the where the K values end. So the H values start in Z6, the K values end in Z3. And so now let's ask ourselves, what is K mod H, K composed of H of 0 mod 6. So that's K of H of 0, but where did H take 0? 0. So that becomes K of 0, but where does K take 0? 0. Then let's look at K composed of H of 1 mod 6. So 1 goes to 1, right? And then over here, the K takes 1, 2, 2. So that's going to go to 2 mod 3. So then you tell me, K composed of H of 3 mod 6. Yeah, well, K of 0, which is equal to 0. And then K composed of H of 4 mod 6.
Okay.
4 goes to 1, 1 goes to 2. Yay! So
you
we're
just
at
have to
5.
follow.
Yes.
Give it.
So 5 goes to 2, and where does 2 go to? 1. Yep.
So basically, they just
Oh, I skipped 2.
Basically, you look at what's given at the top.
and then follow that pattern.
Yep.
Okay.
You so let's see. I have a pointer someplace. Yeah. No, I don't want that. Where's my pointer? There we go. So you can sort of see my little pointer right here. If you go up here, the 2 up here, 2 goes to 2, and then you have to go down. The 2 goes to 1. So that means that we're going to have 1 mod 3. Yeah,
Sorry.
you could.
You just like pointing at
It's supposed to have a better pointer than that, but there you go. Can you do that, by the way, on your homework? K composed of H. What would
Yeah.
K inverse be?
The opposite.
Yeah, so you would start at 0, go to 0, K of 2 goes to 1, and K of 1 goes to 2. K inverse is equal to K. It's the same function.
So you just stay with it.
No, you say K inverse of the last is equal to the first. K inverse of the last is equal to the first. K inverse of the last is equal to the first. You switch them. What would K inverse composed of K be? It'd be the identity. It's going to take 0 to 0. K takes 1 to 2, and then K inverse takes 2 back to 1. So it would take 1 to 1. K takes 2 to 1, and then K inverse takes 1 to 2, so 2 would go to 2. So K inverse composed of K is going to be the identity. Okay. This is a pre-calculus question. Let f of x equal x squared, g of x equal to 1 over x minus 4. What is the domain of f? Yep. What's the domain of f composed of g? Well, sorry, g composed of f. Well, notice I didn't ask you what the domain of g was. What's the domain of g? Yeah. So the domain of g composed of f is you take everything from the domain of f so that the answer doesn't equal 4. So we're going to take x squared not equal to 4. That means x is not equal to plus or minus 2. That's our domain of g composed of f. You start with your domain of f, and then you restrict it so nothing breaks in g. Yeah. And you guys find that relatively easy now. But when you were in pre-calculus, that was like the most hardest problem I can give you. Well, we like it a lot better than proofs. It's a lot easier than proofs.
Well, that's extremely true. Sometimes the simple stuff is what confuses me.
That's true. That is very true. I can try and make a test easy for like pre-calculus, and it'll be so easy that it's hard. But if I just make it hard like I made the review, then they'll do fine on it. Just don't make it easy.
No, overthink.
Then they'll overthink.
But if we give a really hard review,
And then you get to the test,
you get to
yeah.
the test, and the test is like super
Oh.
simple, but it's similar to the stuff that you did on the review,
Then you
And
try
you'll
and
think-
do it all.
that it's similar to the review, and then you'll think that it means that certain thing, and you'll overdo whatever you're trying to do.
That
Like
happens
the
with them.
reverse psychology.
It is. But if I give a really easy review
And then a hard test.
and a hard test, it's worse.
That's
Oh,
not fair.
That doesn't happen. Yeah. So the last question, are the two domains the same here? Domain of f and g composed of f? No. There is a further restriction added on to that. Okay. This one was kind of an interesting little proof.
It's just associated.
It's just associative. They broke the proof up into two things. What do you have to do to show functions are equal? Domains are the same, right? And then two, the images of x is the same. So h composed of g composed of f of x has to be equal to h composed of g composed of f evaluated at x. They have to have the same image for that x value. So this phrase right here, I say show the images are the same. That's the two things you have to do to show that your functions are equal. Show that you have the same images.
Sure, image is.
Images range. You're plugging in a domain value. Yeah.
Why do you say image instead of range?
Well, because I want the image for that particular x. I don't want all possible values. Yeah. So the images, suppose you had f of x equals to x squared. And then I would say the image of x equal to 2
Gotcha.
is 4. It's the particular value
Function of.
Yeah. for that particular value. When I say range, I mean all possible values, no matter what you plug in from the domain.
That makes sense.
Yeah. So when they did part 2 on it, they actually did it by just expanding what the composition was. They didn't say that there exists a Z. They said H composed of G composed of F of X was equal to H composed of G of F of X. And then they said that's equal to H of G of F of X, which is equal to H of G composed of F of X, which is equal to H composed of G composed of F, evaluated at X. And that's all they did. Now, how come they can do that? Because I'm pretty sure that last time we talked about showing functions are equal, we showed that they were subsets of each other. Same thing. This is an alternate way of doing it. This is saying that if you're plugging in this X right here, then that's the same thing as saying that X, Y is an H composed of G composed of F. That's what that is saying. So it's just a different notation. It's a different way of doing it. But it's one that I think we're more familiar with. If we just keep plugging in the X's, we know what to do with that. When we talk about the X comma Y being an element of something, we're not quite so sure about it. So you can use this method to show functions are equal. That's completely all right. Yeah. I'm actually not going to prove that one for you, and I'm not going to prove the next theorem. We have to talk about the last theorem. This is just saying when you compose a function with its inverse, you're going to get the identity. What's the difference between these two identities? Identity sub A. No, it's what the domain for the identity is. So the identity for A is A, the domain for that is A, and the domain for this identity function is C. So that is the domain. They're just denoting what the domain is for the identity function. Don't let it confuse you. What's your question?
If the function is A going to B, how could we see which way to B?
F takes A to B. The range of F is a subset of B. Remember, for a function, it has to take all of the domain to some.
So we know C is
Yeah. That's what we know. And we actually are going to use more range than the codomain, because we just really care what the image of F is. We really don't care what any of the extra points are, especially when we start trying to take inverse functions of it. We need to know what the range was. So mostly we just talk about what the range is. Okay, this was from the quiz. Let F be a function from a set of reals to the reals whose domain includes an interval I. We say F is increasing on I if and only if for all x, y, and I. If x is less than y, then f of x is less than f of y. It is decreasing on I if and only if x less than y means f of x is greater than f of y. What happens if it's equal?
This concept, there's no slope.
Most books allow this right here.
But
It doesn't matter which way we,
Why would it be considered decreasing if it's equal?
they just allow the equality because it's easier to prove with a less than or equal to than it is a strictly less than.
Oh, yeah, you have to say it.
Yeah, how do you know it's exactly less, how it might be equal? That's hard to argue that it's not equal, but equal or smaller is easy to argue. It allows you to have more options. So that's
So
why,
it's basically just ignoring the fact that it wasn't.
not necessarily. So horizontal lines are both increasing and decreasing, and mathematicians are happy with that. Not a problem.
Wait,
Horizontal lines can be both increasing and decreasing. In every book except this one. This is the only book I know of that actually makes a strict inequality. We usually allow the less than or equal to, greater than or equal to. And when we get to it,
It's, there's a,
we will see that kind of thought.
we'll look at it. Okay, so we have a homework problem. What is that homework problem? 17. Nope, it's not 17. 13.
Is it just like this one?
No.
I'm in the wrong section.
Oh,
It would help if I were in the right section. No, I took 13 off. You'll see that I took all of the restricted function stuff off. I didn't figure we were gonna have time to get to it. Okay. You have to do 17 B and C on your homework. It says prove or give a counterexample. I'm going to skip this lemma, but I'm going to use this space, and we're going to look at the second one. If F and G.
Wait, so this would be 17C?
Mhm. If F and G are decreasing on I, and F composed of G is defined on I, then F composed of G is increasing. A lot of people actually call it fog. So here's a question. True or false?
For which function?
For that C, it says if F and G are decreasing on I, and F composed of G is defined, then F composed of G is increasing on I.
you cannot say that.
Yeah, you can. Assuming you can say it. Which way do you think it's going to be?
Both ones do.
So after this, you get this, you compose it, it's gonna be decreasing. It cannot be.
If you're sticking one into another, it should still be decreasing.
But if you've got F.
Because you're plugging G into F and it's still decreasing.
Exactly.
Wait, what?
If f of x is negative x, if g of x is negative x, we propose to be
So it
True.
depends.
It is true.
It's not always true.
Yes, it is. I'm going to prove it for you.
It's always true.
Always true.
Okay.
Just reading it, it makes sense that you decrease it.
That's what you think. That's your gut reaction. You want it to be decreasing because, you know, the two original functions are decreasing, so the composition should be decreasing. But it's not. It's increasing. So, what's the hypothesis for this, by the way?
Suppose F and G are decreasing functions on I.
You can suppose, you can assume. You can let. They're all synonyms. And assume
That is
F composed of G is defined. Really?
Wait, what?
No, they're predicting it that early. It probably won't happen. I'm cynical. Tornadoes only happen at the drop of a hat. They're not predictable. Okay,
Very true though.
it is. So, what do we know about our hypothesis? Suppose F and G are decreasing functions. So that means we need to let X be less than Y in I. Well, I've got an assume. I have a suppose and assume, so I need to use a let.
How can we assume X is?
Can't we just make up two functions right away word just
Nope.
How can we assume
You have
that?
to show it for all functions. If you just show it for two functions, then you still have an infinite number to go. Yep.
How can we assume that X is less than Y?
We just need X to be less than Y for the definition. What's our definition of decreasing? If x is less than y, then f of x is greater than f of y. Yeah, so that's why. So let x be less than y and I. Yeah, you can use A and B. You want A and B?
Well, X and Y make sense, they're points.
No,
They're not.
if we use X and Y, it's so confused, just use A and B.
We got A and B. Okay, so then tell me about the relationship f of A and f of B. Who's bigger?
Or no.
F of A. Because it's getting smaller, so if you think about this right here, here's A, here's B, has to be up and going down. So f of A has to be bigger than f of B.
We said it's less than 80.
Mhm.
Right,
Yeah.
but for a decreasing function, the function of A is greater than the function of B.
You're going from left to
For an
right.
increasing function, the function of A is less than.
And so then tell me about g of f of A and g of f of B. If you know that f of A is bigger than f of B, then if you are going from right to left and plugging in your f functions, here is going to be your f of B, and here is going to be your f of A, and they could be less than or equal to. It could be the same point. If it's the same point, then it's equal. And if it's different points, then if we want our function decreasing, the g of f of B has to be bigger than g of f of A.
Wait, say it again,
Whoa. Why did
Okay.
they put stops?
and then again.
Because when you're graphing it, if your horizontal line becomes the f values, which is the f values are what you're plugging into g.
Yeah. it's just
So then you have f of B before you have f of A on your x-axis. And so then your g is still decreasing. So g of f of B has to be bigger than g of f of A.
You flip it side, and flip back.
So then what that tells us is g composed of f of A is less than or equal to g composed of f of B, which says g composed of f is increasing. And you're going to conclude. So my little 3 dots mean you're going to conclude. And there's our, that makes sense? Homework problem, done.
Yeah.
Your part B then is going to be false, and so you have to give me a counterexample. This is where, Dalton, you get to invent your functions. So give me 2 functions that work for part B, okay?
That don't work.
That don't work. In other words, they're going to contradict what you have in part B. They have to satisfy the hypothesis, but they contradict the conclusion.
That could be short.
Yeah, that's not
Oh,
a
yeah.
proof, it's a
It's
counterexample.
just an example.
Oh,
That's all you're doing. Okay, we are done for today. Yep, class is over. That one's always a fun one. I like doing increasing and decreasing functions.
it's weird.
It's
though.
a
It's really like
counterintuitive.
decreases. It's just-
Yeah, the composition of it increases.
I don't know what I'm doing over today.
I don't know, yeah, I have to go.
Oh, well, I got all of it. I got all of it.
I need to figure out what I have to do for the project. Is that what's there?
Yeah, she is.
I expect myself to be there. Okay, that's good. Okay. Then nothing to do with class. Everything's been kept.
Oh, let me save this before I forget.